Next, we're gonna learn about the recursive implementation of backtracking. In the previous implementation, we used 4 for loops, but our problem is n queens. So actually the number of for loops are gonna be dynamically changed. To achieve that, recursive implementation gonna give us more flexibility. And this is our implementation for backtracking. With the n-queen problem, you will see that we reuse a lot of code from iterative implementation. In fact, the bounding function that we have is exactly the same. Here I already run this recursive function, and as you can see, the output and the result are exactly the same with our iterative implementation. It's killing the same branches, and they both have the same result. And iterative or recursive implementation, we only have 2 steps in implementing backtracking. I'm gonna break it down step by step here. So for backtracking n queens, recursive implementation, we're gonna take in the number of the queens. We're gonna initialize the result array, where we're gonna have our final result, and we initialize a temporary result. This is the node collection for each of the depth of search. And it looks like this. We have 4 queens, and we have the position of each queen. For example, we have 103. That's gonna be queen 1, row 0, and column 3. Next, we're gonna have a depth of search. Then we run this depth of search, and then we return the result. The structure of the recursive backtracking implementation will always look like this. Now we're gonna fill in this depth of search function. With step 1, we're gonna do the full branch out. This recursive function is doing a depth of search, and this base case condition is to collect the final result when the depth of search finishes a branch. If we look closely here, we will see that we always process first, and then we call the depth of search. So these 2 lines here is pre-ordered tree traversal that we have learned before, and depth of search itself is pre-ordered tree traversal. Here we have the for loop of n queens. It's gonna dynamically do all the branches for all the queen options in one row. Now this part right here is responsible for the name of the backtrack, because we hit this line where we have seen a base case. For example, right here, we are at the end of the depth. So we backtrack to the previous node by popping out the most recent queen placement. In this example, that's going to be this queen placement, queen 4, cell 30. And we decrease the queen number so it can come back to queen 4 again and try the next queen placement, which is queen 4, cell 31. So popping and coming back. This part right here is the reason why this algorithm is called backtracking. With this logic, our step 1 full branch out is done. We can test it by running this algorithm and have a look at a few results. Now remember, by this step full branch out, we're gonna collect all possible placement of the 4 queens. And the first one is queen 1, 0, 0, queen 2, 1, 0, queen 3, 2, 0, and queen 4, 3, 0, which is what we have here. And the second one is this depth first search, ending at queen 4, 3, 1, which is this one. And another test is, we can see the length of the total possible solution, and that is 256, which is the total way of setup that we have before. So now we know that our step 1 is correct. We're gonna continue to step 2, which is using the bounding condition that we have from the problem statement that queen cannot attack each other to kill off the unnecessary branching. And you may have noticed that this logic for our recursive implementation look exactly the same with the iterative version. The only difference is we stop the recursion by returning here instead of returning true or false. So we're gonna get this logic and put it here on top of the recursive depth first search, because the bounding condition is actually one of the base cases where we're gonna stop the recursion. So if we run our algorithm again, this is the result that we're gonna get. It's killing the same branches with the iterative version, and it's having the same result with the iterative version. Now for this recursive implementation, we now can control the number of the for loop, which is the number of the queens. So if we change this into 9, we now have the result of 9 queens in the 9x9 chessboard that they're not gonna attack each other. And we actually have 352 set up for 9 queens that satisfy our bounding conditions. So you can see backtracking is really easy to use. The most tricky part is probably this one, doing a depth first search to collect the nodes. And the procedures only had 2 steps. full branch out, and killing the unnecessary branching. Now remember, when you do the full branch out, with depth first search, keep the queen number small to test if it's correct or not. And then you can increase the queen number to see the beauty of the implementation. Next, we're gonna see the characteristics of problems that can be solved by backtracking. And it's actually a lot. Backtracking is powerful, and it's really simple and easy to use. It's too simple, it only have 2 steps. Step 1 is to use depth first search to branch out and build all possible outcomes. Step 2 is to use the bounding conditions to remove the unmeaningful branching. And what's so easy about this is these bounding conditions are basically the condition that already given from the problem statement. So we don't really have to do any heavy logical thinking. We only need to interpret the condition in the problem statement into code, and then we are done. Now, typical problems that can be solved by backtracking is virtually any problems because it's a brute force solution and it's a smart brute force solution, so it's performant. Some of the typical problem types are sequential decision making problem. Our problem N queen is actually a sequential decision making problem. For each of the steps, we have a decision to make. For example, for this one, our decision is to choose where to place queen 1, and the next one is where to choose to place queen 2, and so on. And if we think about it, that's actually what life is about. We have a sequence of decisions, and the decisions that we're making right now, for example, choosing queen 2, had a relationship to the decision that we made before, which is choosing queen 1. And we just saw backtracking solve this problem very nicely. That means we can solve a lot of decision-making problems in real life. We can simulate different situations, for example, buying, selling stock at different times, and get the best profit out of it. Another typical problem that we can solve with backtracking is problem that logical thinking create many choices, and for these kind of problems, try or then choose is more suitable than logical thinking. That's basically the same thing with our N queen problem here. There's not a lot of logical thinking here. If we humans solve this problem without a computer, what we usually do is we're just gonna try placing the queens in different positions and apply the condition here to choose the place for the next queen and try again if that pattern doesn't create a correct result. So there's not a lot of logical thinking here. It's just trying different ways and choosing the suitable one. It can be very tedious for a human if the number of the queen get large. For example, 100 queens or 1,000 queens. It's virtually impossible for a human to patiently do it. But machine, the computer, can patiently do it with no problem. So if you can really understand this point of backtracking and use backtracking fluently, you and the computer combined together are one and can virtually solve any problem. Let that feeling and thinking sink into your brain for a moment. Now, another typical problem that can be solved by backtracking is problem that we solve by step. For example, step 1 we do ABC, step 2 we do BCD, and so on. Then the step-by-step solution can be created by branching out with depth first search. And with that, we can use backtracking to build up the solutions and solve the step-by-step problem. Now, to summarize backtracking iterative implementation, we have step 1, list all possible options, that is using nested for loop to build up the final state. So nested for loop is actually depth first search. For example, here we have 3 nested for loop, and we're collecting the data step by step after each loop until we have the final state. In N queen example, the final state is when we have a position of all 4 queens or N queens. For step 2, we create the bounding function. The bounding function is going to take in the state, which is the position of the queen we collect along the way, and apply the condition from the problem statement to decide to stop branching or continue to branch. For step 3, we put the bounding function in each of the state creation. So for each of the for loop, we check the state. If it's not necessary to continue to branch, we're gonna stop branching and move on to the next element. And we apply the bounding conditions in every new state, which is the new queen position in our problem. Finally, the state that finally can branch to the full depth are the state that pass all the bounding condition, and it can go to our result rate. And that's how we do backtracking with iterative approach. for backtracking with recursive approach, we're gonna have a depth first search. And step 1 of the depth first search is to collect all possible outcomes. Then step 2 is one of the base cases when we stop the branching of unmeaningful branches on the top. And this part right here, popping the results and returning to the previous node, is what is called backtrack. We hit a dead end, we backtrack. We hit a dead end, we backtrack. And that is how we do backtracking with depth first search, recursive approach. Next, we're gonna summarize our backtracking. Backtracking is really powerful, so you can actually use it to any problem classes. For maximization and minimization problem, which are very desirable in information problem, we now have a powerful tool of backtracking. For finding all option problem, backtracking can surely provide an answer because it's a smart brute force solution. For finding most optimal solution, it can be sorted longest, max, mean, or whatever condition that we need. We can put it in the bounding condition and apply backtracking to solve our problem. The time complexity varies a lot. We always know the time complexity of the full branch out, but we never know how the bounding condition is gonna stop how many branching. So time complexity in backtracking varies a lot. And it's usually an estimation, not a solid calculation, based on how strict the bounding conditions are. That is all for today's tutorial. Thank you for watching, and I will see you in the next video.